Hello everyone, welcome to today's lecture. Today we are going to do differentiability for two variables and three variables. So first, before starting, for differentiability of two variables, we understand what it means in one variable. So in one variable, what we had was there was an interval AB which was a subset of R and which is tending to R. So we have a function in this way, and we take any interior point of this interval I. If this is interval AB, if we take any interior point, let us say C belonging to A, then we say that f is differentiable at C if we have limit h tends to 0 f of C plus h minus f of C divided by h is equals to f dash C, or we could even say limit x tends to C f of x minus f of a C divided by x minus C is equals to f dash C. If this limit exists, then if this limit exists finitely, then f dash C is said to be the derivative at that point C. Similarly, if we proceed with similar argument, so we can define for two dimension. For two dimension, what changes is the domain changes. Now it is in R2 to R. So what happens is we have a point somewhat like this in the domain, so everything else remains the same. So what we have is limit x y tends to x naught y naught, same thing, x y tends to x naught y naught, and what we'll have is x y minus f of x naught y naught minus, here what we have is the partial derivative x minus x naught f x x naught y naught plus f y y minus y naught f y x naught y naught. So we need to add up the partial derivative in this case, x minus x naught whole square plus y minus y naught whole square. So let us understand by the definition what it is written. Let f be a mapping from D, which is a subset of R2 to R, and let x naught y naught be an interior point of D. Then f is differentiable at x naught y naught means that there are two numbers fx partial derivative with respect to x at the point x naught y naught and partial derivative with respect to y at the point x naught y naught, such that limit x y tends to x naught y naught f of x y minus f of x naught y naught minus x naught fx x naught y naught minus y naught fy x naught y naught divided by root over the distance between the point and the function, the 2 points, is x minus x naught whole square plus y minus y naught whole square is equals to 0. If this is 0, then we say that the function is differentiable. So let us go through one theorem which says if f is differentiable at any point AB, then f is continuous at that point. So differentiability implies continuity. So we do not go to the proof. The proof is simple. We now go for total differential. So what is total differential? Total differential is defined by df, and it is partial derivative of x with respect into dx and partial derivative of y with respect to y and into dy, or that can be written as del f by del y dy. Now we understand one more point, which is del f. Del f is the functional value at x naught y naught minus the functional value at x naught y naught. And from the above definition, if we replace the points, what we get is limit x naught y naught, xy tends to x naught y naught, and what we have is this is del f, so del f minus df divided by root over x minus x naught whole square plus y minus y naught whole square. So this must be 0 in order to be differentiable. Now if we take x minus x naught is equals to h and y minus y naught is equals to k, then this relation changes to limit h tends to 0, k tends to 0, del f minus df divided by root over x square plus k square is equals to 0. So this is another relation for differentiability. So we now understand with an example. So the example says the function is f of xy is equals to x into y. So we need to find the differentiability at any point. So here what we see is del f is x plus h y plus k minus f of x y, which will be x plus h into y plus k minus xy, which is hy plus kx plus hk. xy and xy will cancel, and again df is hfx plus kfy. Here h, if we find fx at any point, so it will be with respect to x, so it will be y, and fy at any point will be x. So h y plus kx. Now limit h tends to 0, k tends to 0, del f minus df divided by root over h square plus k square. If this is 0, then we say that the function is differentiable at that point. In this case it will be everywhere. So it is kx plus hk minus hky minus kx. Sorry, here it will be kx whole divided by root over h square plus k square. So this is limit h tends to 0, k tends to 0, hk divided by h square plus k square. As we have already done, this value is 0 and hence it is differentiable. We move on to another example. So here we have f of x is equals to xy divided by root over x square plus y square when x square plus y square not equal to 0, and 0 when x square plus y square is equals to 0. So we check for the continuity by epsilon delta definition. So at the point 0, 0, by intuition we take, so at the point 0, 0 the functional value is 0. So f of xy minus f of 0, 0 is this xy divided by root over x square plus y square minus 0, which is xy divided by root over x square plus y square modulus. This is equals to modulus of x plus into modulus of y divided by root over x square plus y square, which is less than equal to root over x square plus y square root over x square plus y square divided by root over x square plus y square. Since modulus of x is less than equal to root over x square plus y square, and modulus of y is less than equal to root over x square plus y square, so one of the root over x square plus y square cancels and we get less than epsilon. So if we choose delta equal to epsilon, we find that the epsilon delta definition for continuity is satisfied, hence the function is continuous at 0 0. Now we find the partial derivatives. So here the partial derivative f of x at 0 0 is limit h tends to 0 at f of h comma 0 minus f of 0 0 divided by h, which is 0 by h, which is 0. So here the partial derivative with respect to x is 0. Similarly, we can see that the partial derivative with respect to y is also 0. Now, thus both the partial derivative exist at 0 0. In fact, del f, which is f of xy minus f of 0 0, is hk this is hk. F of hk minus f of 0 0 is hk root over h square plus k square, and df, which is hfx plus kfy, is 0 since both the partial derivatives are 0. Therefore, limit h tends to 0, k tends to 0, del f minus df divided by root over h square plus k square is equals to limit h tends to 0, k tends to 0, hk divided by h square plus k square into 1 by root over h square plus k square, which is equals to limit h tends to 0, k tends to 0, hk divided by h square plus k square. Putting k is equals to mh, we have limit h tends to 0, h square m divided by h square 1 plus m square, which is m 1 plus m square, which is different for different values of m. Hence the limit does not exist. So we can conclude that f is not differentiable at 0 0, although it was both the partial derivatives exist as 0 0. Now the question arises, when will we get we understand that the function is differentiable at a point. So for this we state a theorem. So the theorem states sufficient condition for differentiability: if AB be a point in a domain of definition of a function f of two independent variables x and y, such that one of the partial derivative f of x or f of y exists and the other is continuous at AB, then we say that the function is differentiable. So what this definition says is, if AB is any point in the domain of the definition of any two point in the domain, so a function f which is from D to R, D subset of R2, is said to be differentiable if one of the partial derivative del f by del x exists at AB and the other del f by del y is continuous at AB. It may so happen that either del f by del y exists and del f by del x is continuous. Any one must exist and the other must be continuous. Then we say that f is differentiable at AB. I hope we understand the theorem. So after this theorem we have a small note. The note states that the condition which was stated in the theorem is sufficient, but it is not necessary, and we illustrate this by an example. So we see an example which will say that the condition what we have done is sufficient, but it is not necessary. So here what we have is f of xy is equals to x square sine 1 by x plus y square sine 1 by y when neither x is equals to 0 nor y is equals to 0, x square sine 1 by x when y is equals to 0 but x not equal to 0, y square sine 1 by y when x is equals to 0 but y not equal to 0, and 0 when x is equals to 0 and y is equals to 0. So here what we need to show is the condition is sufficient but not necessary. So here what we show is, first we find the partial derivatives. So here f of x at any point will be 2x differentiation with respect to x sine 1 by x then cos 1 by x when x is equals to 0. I show you the mechanism. So we had f is equals to x square sine 1 by x plus y square sine 1 by y. We take y to be constant and differentiate with respect to x. So what we get is f of x at any point xy will be, first we differentiate this, then we differentiate this. So differentiating this first part, what we get is 2x sine 1 by x is kept constant. Then what we need to do is we need to keep x square constant, sine 1 by x. Sine 1 by x will give cos 1 by x dot. Now 1 by x is a function, so we need to differentiate this, which will give minus 1 by x square. So this plus and this minus will be plus 0. This is a function this does not has any function of x, so this is 0. So what we get is 2x sine 1 by x plus, now this negative sign and this positive will change to negative, this x square and x square cancels, so we get cos 1 by x. So this is the mechanism. And if we have function at the point 0 comma y, so surely this part is 0, hence we'll get 0. Similarly, f of y at the point xy will be 2y sine 1 by y cos 1 by y, and if we have y is equals to 0, we'll get 0. So from here what we see is, thus neither of f of x nor f of y is continuous at 0 0. So what we get is both of them are not at all continuous at 0. This is because cos 1 by x or cos 1 by y does not tends to 0 as x tends to 0 and y tends to 0 respectively. Both fx and fy exist at 0 0, but none of them are continuous there. Now we check for differentiability. So now, before stating this, we need to have one notion for differentiability. So let us first do this. Notion of differentiability. A function f is said to be differentiable at xy if we can express the increment del f is known as increment, in the form del f is equals to f of x plus h y plus k minus f of xy, which is equals to ah plus bk plus eta 1h plus eta 2k, where a, b are independent of h and k, and eta 1 and eta 2 are function of hk such that eta 1 eta 2 tends to 0 as hk tends to 0 0. So what this is saying is, if we can express this increment in the form this, then we can say that the function is differentiable and this eta 1 and eta 2 must tends to 0 as hk tends to 0 0. So let's see here. So here what we have is the increment del f. So the increment del f is equals to f of 0 plus h 0 plus k minus f of 0 0 is equals to f of hk minus f of 0 0. This is simple. So now what we do is we put the value. So this is h square, h, k both not 0, so what we need to put h square sine 1 by h plus k square sine 1 by k, and this is 0. Now we can express this as 0 dot h plus 0 dot k, since the partial derivatives are 0, plus h into sine 1 by h, sine 1 by h, plus k sine 1 by k. We can express it in this form, and we know that 0 is f of x at the point 0 0 dot h plus y at the point 0 0 dot k plus eta 1 h plus eta 2 k. So here what we see is eta 1 is h sine 1 by h, which tends to 0 as h tends to 0, and eta 2 is k sine 1 by k, which tends to 0 as h tends to 0. So this shows that fx is differentiable at the point 0 0, but none of the partial derivatives were continuous at the point 0 0, hence stating that the theorem which we had stated was necessary but not sufficient but not necessary. We again try to understand the notion of differentiability. A function f is said to be differentiable at xy if we can express the increment del f in the form del f is equals to f of x plus h y plus k minus f of xy, which is equals to ah plus bk plus eta 1h plus eta 2k, where a, b are independent of hk and eta 1 and eta 2 are functions of hk, such that eta 1 and eta 2 tends to 0 as hk tends to 0 0. In the previous example we saw that we could express eta the increment delta f by this form, where we could find two functions eta 1 and eta 2 which tend to 0, which were functions of h and k, and which tend to 0 as hk tends to 0 0. Hence we could conclude that the function is differentiable. In a similar manner we can go for 3 dimension. So in 3 dimension, a function f of 3 dimension, 3 variables x, y, z defined over a domain D subset of R3 is said to be differentiable at a x, y, z belonging to D if the increment del x, del y, del z of x, y, z produces a total increment del f which is equals to x plus delta x, y plus delta y, z plus delta z minus f of x, y, z, having the form del f is equals to a. So it's similar to this. Here a delta x, bk, b delta y, and c delta z, eta 1 delta x, eta 2 delta y, and eta 3 delta z. So here again a, b, c are independent of delta x, delta y, and delta z, and eta 1, eta 2, eta 3 must be a function of delta x, delta y, and delta z, and thus tends to 0 as delta x, delta y, delta z tends to 0 0 and 0. We do one more example for differentiability. So here we check for the sufficient condition of differentiability. So the example says, examine the condition of the theorem on the sufficient condition of differentiability to investigate whether the function defined below is differentiable at 0 0 or not. Here the function is f of xy is equals to xy x square minus y square divided by x square plus y square when xy not equal to 0, 0 and 0 when xy equal to 0, 0. So we need to investigate. So here what we do is we first find the partial derivative. So f of x at the point 0, 0 will be limit h tends to 0 f of h comma 0 minus f of 0, 0 whole divided by h, which is limit h tends to 0, 0 by h, which is 0. Similarly, we can get f of y is equal at the point 0, 0 is equals to 0. Now again, when x and y both are not 0, then what we get is f of x at the point xy is, so we now find the derivative, partial derivative with respect to x. So here what we see is if we multiply xy into x square minus y square whole divided by x square plus y square, this is the function. So we can write this function as x cube y minus xy cube whole divided by x square plus y square. So now we try to partially differentiate this function. So what we get is x square plus y square whole square u by v form, and this will be 3x square y minus y square v del u, v is x square plus y square, minus 2x x cube y minus xy cube. I hope you understand. So what we did is differentiation of u by v is equals to u v del u minus u del v divided by v square. So we did this thing. So after multiplying, what we get is 3, this and this will multiply and it will get x to the power 4 y minus 3x square y cube minus x square y cube minus y to the power 5 minus 2x to the power 4y plus 2x square y cube whole divided by x square plus y square whole square. So if we simplify, we see x to the power 4 y here, x to the power 4 y here, so and this is negative, this is positive, so we get x to the power 4 y plus, now what we see is x square y cube, x square y cube and x square y cube. So this is 3 plus 1 4, so this is positive, sorry, this into this is positive, so 3 plus 2 is 5 minus 1 is 4, so this is x square y cube minus y cube, so the remaining is y cube whole divided by x square plus y square whole square. So we get this, and if we find the modulus of this function, what we get is this is less than equal to x to the power 4 y plus 4 x square y cube minus y to the power 5, which is less than equals to x to the power 4 y plus 4 x square y cube plus y to the power 5 whole divided by x square plus y square, x square plus y square whole square. Now as we know that modulus of x is less than equals to x square plus y square root over, so what we get is this is less than equal to root over x square plus y square whole to the power 5 plus 4 root over x square plus y square whole to the power 5 plus root over x square plus y square whole to the power 5 whole divided by x square plus y square whole square, which is equal to 6 x square plus y square 5 by 2 divided by x square plus y square whole square, which is 6 x square plus y square whole divided by 5 by 2 minus 2, which is 6 x square plus y square whole divided by whole to the power. So what we get is f of x at the point xy minus f of x at the point 0 0 modulus is less than epsilon if x square plus y square is less than epsilon by 6 whole square. So we find that function f of x is continuous at the point 0 0, and hence, and we have already seen that the partial derivative, both the partial derivative exist at the point 0 0. Hence, by the sufficient condition of differentiability, we can say that the function f of xy is differentiable. Thank you for watching this video. For any queries, join my group in the description, and here you can find the soft copy of the notes of the lecture and update of the next lecture. Do like and comment and share with your friends. Thank you.